So if we took that line down here and we solving, so we can rearrange it again just to get it the same form as before. We're just gonna get derivative of x2, which is a function of x1, over the derivative of x1 equals minus the utility, the derivative partial utility function with respect to x1, x2, with respect to x1 over the derivative of this utility function with respect to x2. So this is the same as above. Same as before in the sense of both in the chapter as well as kind of when we used when we just took the partial derivatives as opposed to use this like implicit function. The nice thing about using these implicit functions, we can show that the MRS is kind of independent of monotonic transformations. Can show is independent of utility representation. So for example, if we had some function v of x1, x2, which is just some monotonic transformation of this original utility function, then the MRS is minus the derivative of v with respect to x1 over the derivative of v with respect to x2. And we can just use that same kind of implicit functions to know that this is equal to partial of f. So it's how f changes with changes in u. Same thing here. Times how u changes, this utility function changes with x1, how this utility function changes with x2. And so what's happening is these things are going to cancel out, and we get the same thing as above. So it doesn't even matter what kind of utility representation or what monotonic transformation you make. We're getting the same answer, minus the partial of the utility function with respect to x1 over the partial utility function with respect to x2. We're getting that in every case. And we can even kind of show this through the Cobb-Douglas. We can show this really easily through the Cobb-Douglas utility function. So we can represent it with the logs. We saw representing with the logs. We saw representing with this, those exponents. And we can show that the marginal rate of substitution is the same in both, using both of those kind of representations of that particular, those kind of preferences. So for example, let's look at Cobb-Douglas. Cobb-Douglas. I want 2 colons there. Cobb-Douglas there. We'll underline it. All right, so we kind of thought about 2 different ways, and maybe I'll try to do it on each half of the screen here and see if that will work. So the first way we thought about representing, or one way we thought about representing this Cobb-Douglas was x1 to the c, x2 to the d. And we can calculate the marginal rate of substitution, and that's minus the derivative of this utility function with respect to x1 over the derivative of this utility function with respect to x2. So if we did that, we're going to get c, so take a derivative with respect to x1, so c goes down, c minus 1, x1, c minus 1, that remains constant. So that's the numerator, I need a minus sign there. And then taking the derivative of this with respect to x2, we get d times x1 times c, and x2 d minus 1. We can simplify this to being, so x1 to the c is in the denominator, so we can kind of subtract that. So it's x1 c minus 1 minus c, which is a minus 1. And so we end up getting minus c x2 over d x1. you have to play around those exponents, right? Like we're dividing x2 to the power of d divided by x2 to d minus 1. Well, that's like subtracting, d minus d minus 1, which ends up being 1. So that's why x2 is in the numerator. x1 to the c minus 1 minus x1c is just equal to x1 to the minus 1. Well, x1 and minus 1 just puts it in the denominator. So that's what's going on there. Hopefully that's not too bad for you to rearrange a little bit in your head. Now, remember, a different way of representing these Cobb-Douglas utility functions was with that log, right? Ln of c times the ln of natural log of x1 plus d times the natural log of x2. Well, we know that the marginal rate of substitution is the partial minus the partial of this utility function. And I can call it v here if that makes it a little bit better. With respect to x1 over the derivative of this v function with respect to x2. So we're taking the derivative of this with respect to x1. Remember, the derivative of the natural log of x1 is 1 over x1. So what this equals is minus c, just put in the minus already, over x1. That's the numerator here. Now take the derivative of the same function with respect to x2. Well, that's d over x2. Again, the derivative of the log of x2 is 1 over x2. You just got to remember those logs. Well, we have a fraction over a fraction, so we can like flip it and multiply it, and we're going to get the exact same thing. So notice, I'm just trying to show you that the marginal rate of substitution is independent of like the form we chose for this utility function, depending, it's independent of like the monotonic transformation we make to this utility function. So remember, these are just two monotonic transformations of the same kind of preferences. And all I'm saying is they're going to have the same marginal rate of substitution. Their marginal utilities may be different, but the marginal rate of substitution, or the ratio of these marginal utilities, will be the same.